Did I ever tell you what happens if you have a metal sphere and you put that metal sphere inside of an electric field? Let's say there's an electric field facing that direction. Now the thing about this metal sphere is it will become ionized. If the electric field's facing that direction, let me just draw you one electric field line up here and another electric field line down there. If the electric field is facing that direction, that means there must be some source of it over here, some positive charges, and some sink for it over here, some negative charges. So you can bet that this sucker will become polarized, and in fact you'll get some positive charges stacking up over here and some negative charges stacking up over on that side. Yeah, that's polarization. And the reason polarization happens is these field lines that would have been coming in here can now terminate on the negative charges that they see right here. And those field yeah, if this had been a uniform field, it would have been all parallel lines, but you see they come in there and they stop. And inside the conductor, well, inside the conductor, our electric field is exactly zero because that's one of the definitions of an ideal conductor. Then these guys right here, these positive charges, well, they get to start electric field lines, and those electric field lines would then go on forever this direction, and we'll be back to the situation of our uniform electric field if you get some distance away from this polarized conductor. So polarization is a really wonderful thing, and I guess what I mean by a conductor is that a conductor can perfectly polarize. This sucker has all negatives over here to completely prevent the entry of any electric field lines. And over here, there are enough positives to completely prevent the entry of any electric field lines. So the electric field just stops here and then begins again there. The reason that nature prefers to do this is electric field lines cost energy. In order to maintain an electric field in space, that requires energy. So notice, and here's another example of that, nature really prefers, if you've got a plus charge and a minus charge, it's got all these electric field lines that exist here. You've got electric field lines here, and here, and here, and here, and the electric field lines would rather not exist because it costs energy for them to exist. So what is that force then? The force that we think of as Coulomb's law is truly nature trying to minimize the potential energy of the system, and in order to minimize it, it has to get rid of this electric field that's pervading all this space in here. And the way to get rid of it is to put these two charges on top of each other, because you know what the electric field looks like if you've got a plus charge on top of an equal negative charge? Well, it is not an electric field. So that's really lovely. If things are neutral, there's no electric field hanging around them, and that's why there's a force that brings those two suckers together. That's not what I wanted to talk about today. Oh, look. Here's Greg Hurd, but he's upside down. Come on, Greg. Turn around. Here's my point. My point is, if you get yourself, hang on, this is probably a big mess. All right. If you get yourself a capacitor, here's a parallel plate capacitor, nearly parallel plate capacitor. If you get your capacitor, and inside of that capacitor, you stick a piece of, can I do yellow? I don't even know if yellow will work. You stick some insulator in here. Now, it's very important that it be an insulator. You don't want it to perfectly polarize, but you want it to polarize pretty well. I've stuck a piece of, I don't know, what do you want to call this? Glass or plastic or pure water or something like that. I guess it could even be paper, but let's say that all of these things could be summarized by one word. It could be called a dielectric. So I'm going to put a dielectric inside of my capacitor. Remember, capacitors have these wires, one on this side and one on that side. And it's a parallel plate capacitor. And, well, let's say we charge the capacitor, right? Well, let me back up just a second. Let me get ourselves an equation. You know that the charge on the positive plate of the capacitor, Q is CV, is the way that I prefer to remember it. So the way of thinking about this could, I mean, you might be a C is Q over V kind of guy. And then that would mean that to hold a given charge on the capacitor, oh no, let's solve it for V. Heck, let's say that that's Q over C. To keep a given amount of charge on the capacitor, you need to put a voltage on it. And I guess if the capacitance is really big, then the voltage you need to keep a given charge on the capacitor is small. And if the capacitance is really small, then the voltage you need to keep a given charge on the capacitor is really big. So voltage can be thought of as an electric pressure we're going to have to put this sucker in quotes, it's kind of an electric pressure. And so it can kind of be thought of as how hard you're pushing. If you're trying to keep a large charge on a small capacitor, you have to push really hard. And if you're trying to keep a large charge on a big capacitor, you don't have to push very hard because the capacitor can efficiently store that charge. So let's take this understanding of capacitance and charge and voltage and such and go over here to this capacitor, which we are presently charging up. Let's put the positive side over here. So we got a 1, a 2, and a 3, and a 4, and a 5, and a 6. And probably at the same time, because there's probably some circuit over here. Did I want to tell you about that? And then I guess I've got myself a battery facing this direction. And somebody hooked up this battery to here and to here. And if this is 1.5 volts, you bet your pants, so you get more pants, that the potential difference between those two plates when everything is said and done will be 1.5 volts. That's cool. Now I'm going to put some negative charges over here because you know charge is conserved, especially with a simple circuit like that. We've charged our capacitor. Now I really don't want this battery in here anymore because it's going to confuse this entire thing. And we'll work with batteries and dynamic interactions like that later, primarily in class. Sorry, internet-only people, you're not going to get this kind of cool stuff. So the neat thing is that this glass or plastic or paper is polarizable. And the dielectric constant, which we're going to use as kappa, kappa is a measure of how polarizable the thing is. So kappa ranges between 1 and infinity. So a large kappa means that it's extremely polarizable substance, and a kappa that's small means that it's not very polarizable or that it's not very dense or something like that. I don't know. Air has a very, very similar kappa to 1. It's like 1.002 or something. And water has a very large polarizability, so it's, well, it's a very polar molecule, right? So its kappa is really big, like 80 or 90 or something. But whatever I put in here will become polarized. Not perfectly polarized, but polarized nonetheless. So let's, how do we do this? Let's put ourselves an electric field. First of all, before I put the dielectric in there, the electric field will be like this. It'd just be a and I'm just going to give you 6 electric field lines going straight across, showing us a uniform field. But after the dielectric is in, the dielectric becomes polarized, which means that this side becomes negative. Not really negative, but a little negative, maybe 4. 1, 2, 3, 4 negative charges over here. And I guess I'll have to go red to stay honest with you. 1, 2, 3, 4 positive charges over here. Now, how do these positive charges get to this side? It's a leaning. The electrons in every single molecule inside the dielectric are leaning away from these negative charges, and they're leaning towards these positive charges. It's not a migration because these suckers must be insulators, but it's a leaning. So inside of the dielectric, we have another electric field. And you know that electric field obeys the principle of superposition, but the electric field caused by the dielectric's surface charge points the opposite direction. And you notice that as a result, you will have a you've got a small electric field inside the dielectric. Now that means that nature is happy. I don't want to argue that it's a zero electric field like it's some kind of conductor, forget about that, but we've got a smaller electric field in there. So something is more efficient. We can actually store charge more efficiently when we've got a dielectric filling the inside of a capacitor. And again, I should say that this dielectric really should fill the capacitor, but I'm drawing it a little bit smaller so that you can see these charges slightly decreased. But if I were to honestly draw myself a capacitor with a dielectric inside of it, let's see, I'll get you some plates. What are we doing? We're doing purple, and then I'm going to put a dielectric completely inside of it. As a consequence, what we've really done is we've decreased, look at this, we've net decreased the charge on this plate. The total charge here is +2 charge. That's on that plate right there. And the total charge over here is -2 charges. And so, although there's still 6 charges that the battery pumped into the capacitor, it only looks like there's 2, because there are these surface charges that are oppositely charged, canceling out that effective charge. So the wonderful thing is, this greatly reduces the voltage needed to keep that charge right there. Wait a second. If to keep a certain charge on our capacitor, we don't need nearly as much voltage, well, that means that our capacitance of the capacitor has gone up. In fact, sometimes quite dramatically. So now I'll enter the typical derivation. Let's look at how big the electric field inside this dielectric is going to be. And that it turns out that that electric field inside of the capacitor is the electric field, if there's no dielectric, divided by kappa. Kappa is that, well, it's sort of like the polarizability. Well, I'll put that in quotes. It's called, what would you call that? I guess you'd call it the dielectric constant. But it should sort of be thought of as polarizability of the dielectric that we've decided to put in there. I guess I should label it strictly as the dielectric constant. If you're hanging around fancy people, then they will want you to call it that. The dielectric constant is a constant for every particular material you'd want to stick in there, and it represents how much the material is able to decrease the field within it. Ooh, okay. So the dielectric constant of a metal is infinity, because the electric field inside of a metal is 0, compared to the electric field outside of the metal, which might be whatever you want. But ideal metals are infinitely polarizable, but I'll guess all dielectrics have some polarizability. But if you're making, well, let's just go on and see what sorts of results this gives us. You know that V is Ed, right? Yeah, I'm a big fan of that too. And we know that the electric field inside the capacitor, if I've got myself a dielectric, is the electric field outside of the dielectric divided by kappa, and then I'm supposed to multiply that by D. Fair enough, so this is the outside electric field times D divided by kappa. But guess what? This thing here, this electric field times D, that would be the voltage before adding the dielectric. And I'm supposed to divide that then by kappa. Oh, so voltage decreases.
How we doing?
Doing great, making a video for the internet.
Oh, okay.
Yeah. So the voltage decreases because remember kappa is greater than 1. And so, if the voltage decreases, then let's find out what's happening to the capacitance. Can we go green for that? Yeah, you should always go green. The capacitance is the charge on the capacitor divided by the voltage. But remember, the voltage has decreased, and now I'm dividing by something that's small. Well, you can see what's going to happen here. It's going to be Q, because the Q is going to be the same, and I'm supposed to divide that by V naught over kappa, and I've got a denominator of a denominator. Well, that's just kappa times Q over V naught. And Q over V naught, you can check what Q over V naught is. Q over V naught is the original capacitance. So we've got kappa times the capacitance that we had before we added a dielectric, and you win. If you have a dielectric of 100, if your dielectric constant is 100, then you've now multiplied the capacitance of your capacitor by a factor of 100. That's actually incredibly awesome. The capacitance increases linearly with the dielectric that we've put in there. And then we can argue that instead of this old equation that we had for capacitance, where it had to do with epsilon naught and area and the separation of the plates, we can then multiply it by kappa. And our book just stops there, but I want to point out to you that kappa times epsilon naught is usually written in most books. This is truly typically written as, instead of kappa times epsilon naught, it's usually written as regular epsilon times area over D. So this is called the permittivity of free space, and this is just called the permittivity. And so we define then kappa times epsilon naught is epsilon, which, automatically put those knots in there, sorry. This is the permittivity of the substance, so you could call it the dielectric permittivity, and this is the dielectric constant, which is a little bit old school. I don't know why our book does that. Bye. Ha! Teased ya. Dielectric breakdown voltage of air is 3 million volts per meter. So if you have a capacitor, this is crazy. If you have a capacitor and the separation between the plates is 1 meter, if you charge that capacitor up so that a voltmeter would read 3 million volts, then the air within that capacitor will break down. That means it will ionize. And when air ionizes, it gets ions, and ions, guess what? Ions conduct electricity. So there will be it's a spark. That means that it's lightning inside of here. And I guess if you had a capacitor and the separation was just 1 millimeter, what's the maximum voltage for that simple capacitor? You figure it out based on the dielectric breakdown voltage of air. Let's see, this is the, oh wait, that's volts per meter, right? That's an electric field. Well, so that's the same thing as 3 times 10 to the 6th newtons per coulomb. If the electric field is big enough, it will separate an electron from nitrogen. Dang, that's polarization. The nitrogen itself becomes permanently polarized where the positive ion that's left is ripped away from the independent electron that manages to escape. And that happens in really, really big electric fields. Let's see if I can find a picture of that polarization in the trash here. Nope, it's gone. I'm finished. Did I ever tell you what happens if you have a metal sphere and you put that metal sphere inside of an electric field? Let's say there's an electric field facing that direction. Now the thing about this metal sphere is it will become ionized. If the electric field's facing that direction, let me just draw you one electric field line up here and another electric field conductor. Then these guys right here, these positive charges, well, they get to start electric field lines, and those electric field lines would then go on forever this direction, and we'll be back to the situation of our uniform electric field if you get some distance away from this polarized conductor. So polarization is a really wonderful thing, and I guess what I mean by a conductor is that a conductor can perfectly polarize. The reason polarization happens is these field lines that would have been coming in here can now terminate on the negative charges that they see right here. And those field, yeah, if this had been a uniform field, it would have been all parallel lines, but you see they come in there and they stop. And inside the conductor, well, inside the conductor, our electric field is exactly 0 because that's one of the definitions of an ideal line down there. If the electric field is facing that direction, that means there must be some source of it over here, some positive charges, and some sink for it over here, some negative charges. So you can bet that this sucker will become polarized, and in fact, you'll get some positive charges stacking up over here and some negative charges stacking up over on that side. Yeah, that's polarization, and the reason this sucker has all negatives over here to completely prevent the entry of any electric field lines. And over here, there are enough positives to completely prevent the entry of any electric field lines. So the electric field just stops here and then begins again there. The reason that nature prefers to do this is electric field lines cost energy.